Good afternoon, everyone. We are the team from National Chenggang University. Today, we are going to present the mission of LIONER. This presentation will be divided into 3 parts: the scientific background, design analysis, and finally, the anticipated results. The LIONER mission is proposed to investigate the lunar ionosphere. As a major part of the exosphere, ionosphere plays an important part in planetary science, and also Moon becomes the perfect laboratory to study the space plasma and its interaction with the Sun, since there is virtually no magnetic field protecting the surface from being bombarded by solar wind particles. The model of lunar ionosphere could be analogous to many extraterrestrial moons and asteroids without the protection of a strong magnetic field. The existence of the lunar ionosphere was first observed by the ground-based radio experiments and later confirmed by Pioneer 7 and Luna 19 and 22. After many years of hard work and many missions probing on the lunar ionosphere, they obtained different results. For example, Luna 19 and 22 detected a remarkable variation of the electron density between the day side and night side, while Kaguya didn't. Therefore, due to limited observations, we still don't know how to form such an ionosphere. There are several mechanisms proposed to explain the formation of the lunar ionosphere. At first, people thought that the ions may come from the photoionization of the neutral exosphere, like hydrogen or helium. However, the prediction on the electron density is about 1 per cubic centimeter, rather than hundreds or thousands measured from the spacecraft. Later, Stubbs proposed the dust electron model and described the levitated dust in lunar sky contributes most of the ions and electrons in the ionosphere. And the calculation meets the result from Luna 19. In 2016, the photochemical model was proposed to explain such a high electron density. The model assumes 10 types of molecules being photoionized into many types of ions and electrons, which will produce more electron than atomic atmosphere, showing the possibility of molecular origin. However, they are still controversial and cannot be determined. Therefore, we need more observation to decide which process really dominates the formation of the lunar ionosphere. Until now, the lunar ionosphere is confirmed. However, its formation, evolution, and variation are still open questions. Therefore, the LIONER mission is proposed to investigate the lunar ionosphere, and it is expected to provide concrete evidence on these questions. To achieve this goal, several quantities have to be measured. First, we want to measure the plasma density of the lunar ionosphere. Also, we want to find out the properties of solar wind particles, the magnetic field, and solar irradiation near Moon, which may all affect the electron density of the lunar ionosphere. In Procyon mission, the spacecraft took photo of the geocorona, the Lyman alpha emission of the hydrogen from the terrestrial exosphere. At the Moon, we also expect to see such a lunar corona from the lunar exosphere. Besides other measurements, the most challenging in this exploration is how to measure the plasma density of a very tenuous lunar ionosphere. Therefore, an innovative technique is proposed. As you might know, one of the most common ways that humanity usually use to probe the ionosphere is by radio occultation. When the electromagnetic wave passes through the ionosphere, it is bending, and the magnitude of refraction depends on the gradient of refractivity normal to the path, which depends on the density gradient. By receiving the signals passing through the ionosphere and analyzing its phase, scientists can know the electron density of the lunar ionosphere. And several missions have successfully observe the terrestrial ionosphere by this technique, including the Formosa 7, which is going to be launched in next year. Several missions have successfully observed the lunar corona by radio occultation with Earth. However, as Imamura mentioned in his paper, the Earth's moon measurements suffer from the contamination by the terrestrial ionosphere and interplanetary plasma. Also, due to long-distance propagation, the signal-to-noise ratio is low. Therefore, we propose a new method to observe the lunar ionosphere, replacing the conventional GPS to a lunar satellite. Here we choose the NASA LRO spacecraft to carry out the lunar occultation. By receiving the signals from LRO, LIONER will be able to acquire a large amount of data with greater distribution. Moreover, the contamination problem faced by other missions can be greatly reduced. To demonstrate the feasibility of the new method, we carefully calculated the possible number of occultation and distribution using the following method. First, we calculate the position of 2 satellites by STK software. Assuming the height of the upper limit of the ionosphere, we check if the signal will pass through the ionosphere and received by the spacecraft using the following criteria. If the distance between the tangential point and the center of Moon lies between the radius of Moon and the ionosphere, an occultation would occur. Then we use the MATLAB to calculate the possible occultation using the radio source from Earth and LRO respectively. The result is remarkable. By changing the radio source from Earth to an existing satellite around the Moon, LIONER will acquire twice more measurements with wider distribution. It is more efficient than performing the radio occultation with Earth-based ground station. Another major challenge is how to fly to Moon. To achieve this goal, we designed a transfer trajectory with the following considerations. First, LIONER will be launched by H2A rocket into GTO orbit. Then, LIONER is designed to use ion propulsion system to save as much as fuel, to allocate more mass to payload and other parts. Third, to ensure we have enough battery power to drive the engine, LIONER will propel intermittently to the Moon. During propagation, LIONER will turn off the engine to charge the battery. To shorten the period of our mission, LIONER will propel for the longest time near Earth apoapsis to circularize the orbit in shortest time. Here is the trajectory of the LIONER project. First, LIONER will be launched by H2A rocket into GTO orbit. In Earth's orbit phase, LIONER will check the feasibility of all instruments. During GTO to round orbit, LIONER will circularize the orbit and ascend. In Earth's escaping phase, LIONER will turn on the engine periodically to escape the Earth's gravity. When it gets nearby the Moon, LIONER will decelerate and be caught by lunar gravity. In circularized phase, LIONER will turn on the engine only near Moon periapsis to circularize and descend. And it will finally get into Moon orbit phase. In Moon orbit phase, LIONER will perform occultation with LRO. To get as many and wide occultation occurrences as possible, we carefully selected the orbit of LIONER to be roughly 2.7 times the period of LRO. The design result is a near-circular orbital plane with an altitude of 2,200 kilometers and inclination of 20 degrees. To summarize the transfer trajectory of LIONER, it is estimated to consume 8 kilograms of fuel, and the time it needs is about 1 year and 8 months from Earth to final lunar orbit. Most importantly, the transfer duration and fuel consumption are acceptable for LIONER mission, making this type of project feasible.
I'm going to present the satellite design. Here shows the system overview. Beside from a normal path of Beside the path from the normal satellite system, there are 5 scientific payloads on LIONER, and they will be introduced later. This part is LIONER. CNDH will receive scientific data from payloads and communicate with the ground station through TT&C. This part is the ground segment. The ground station will receive scientific data from LIONER and transmit the scientific data to the data center for user to perform analysis. Let's move to the satellite configuration. Here, I will only point out the important feature of the LIONER configuration. First, Leica must face to the neither direction to observe the moon. However, IES must face to the right direction to border the field of view. And the thruster must face to the negative right direction to propel LIONER. This shows the deployment unfolding process of LIONER. And the magnetometer must be stretched out of LIONER to avoid interference. The first part of payload is structure and mechanical subsystem. The 7075 aluminum alloy is the leg for the structure. In order to reduce the weight, we choose the honeycomb material for the structure. The natural frequency of the first mode is 236 Hz, which meets the requirement. And the greatest deformation occurs at the fifth mode. This figure shows the stiffness analysis. With an upward acceleration of 5G. The stress distribution on the structure shows only limit deformation. The major purpose of thermal control is to ensure that all instruments will operate at the working temperature. And initial condition of the TCS are all instruments are consist of 7075 aluminum alloy and no conduction, heat resistance, and radiation within the structure. Material applied include NLI, a near-pyrite graphite, and heat pipe. The figures show that all instruments will operate at the working temperature through the mission. The pointing accuracy of ADCS is 0.29 degrees, which is 1/10 of the size of the object. The figure shows the architecture of the ADCS of LIONER. Sensors measure the altitude of LIONER, and the command tone is calculated according to the data. Sensors applied include IMU, sun sensor, star tracker, and gyroscope. EPS is composed of solar cell, batteries, and power distribution and regulation unit. The PDRU allocate power to payloads and subsystems depend on command sent by CNDH. The PDRU ensure that each subsystem and payload to keep on normal current and voltage. This figure shows the battery capacity and power consumption through the circular phase, and this figure shows the situation when the thruster is on and it consumes the largest amount of power, even though the power is enough through the mission. The major function of CNDH includes send command to subsystem and payload, collect and store satellite SOH and scientific data. The major function of CNDH is communicate with the ground station. The data rate for downlink of S-band and X-band are 1200 bps and 4000 bps respectively. The bandwidth of S-band is relatively small, but it is enough to send the SOH data. And X-band is broader and is able to transmit the largest size of scientific data. LIONER is unable to communicate with the ground station all the time because of being shielded by the moon. So the total communication time is 72,000 seconds per day, and the maximum data capacity is 43 megabytes per day, which is larger than the total transmit data amount, which is 40 megabytes per day. This slide shows the link budget calculation, and the margins are larger than 0. The display network are selected for the ground station. There are 3 ground stations located at Canberra, Metairie, and Goldstone.
Okay, now I'm going to talk about the scientific payloads. This is the LIONER circulation receiver, and it was once used by the Nanyang Technological University's VELOC-CI mission. The receiver was originally designed to receive the GPS signal. Therefore, some modifications are needed on the frequency and bandwidth to receive the LRO's S-band signal and comply the RO requirements. This is the IES used on the LIONER to measure the energy spectra of ion and electron. It has been used by the Rosetta mission and had a great success. Besides IES, LIONER also equips a magnetometer which was also used in the Rosetta mission before, for measuring the lunar magnetic field and explore the role in the variation of lunar ionosphere. LIONER equips a camera named Leica, and it was used in the Procyon mission. The recent one has a photo length of 400 mm, which enables LIONER to take the Lyman alpha emission not only on the moon but also the Earth. The SHAP is a tiny instrument that can measure solar UV irradiation to find out the relationship between hydrogen corona and solar irradiation. It was used in the NCKU Phoenix CubeSat, and which is a part of the QB50 constellation. After careful calculation, the power consumption and the total mass of the satellite are both within a safe margin. Because almost all of the payloads and science instruments have been used in other space missions before, the TRL levels are very high for LIONER, which means that the design of LIONER is feasible and worthy to do. Okay, finally, let us summarize our mission. As we introduced, LIONER is such a space mission which aiming on the exploration of the lunar ionosphere, including its origin, variation, and evolution of the lunar ionosphere, and the interaction with solar wind and irradiance, as well as the ambient magnetic field. Also, an innovative technique radio occultation is employed to measure the electron density of the lunar ionosphere with the assistance of NASA's LRO satellites. From the measured result, we are able to understand the past and the future of the lunar ionosphere and also its impact on the communication of the moon and between the moon and the Earth. This will become an important role in the future if the human beings have more exploration activities on the lunar surface or even move and colonize there in the near future, which the inspiration of LIONER mission can attract more people to study on the lunar ionosphere. Thanks for listening.
これより質疑応答に入ります。審査員の方からアドバイス、ご質問等ございますでしょうか。
highly evaluate that you have responded to all of our questions and comments just one by one. And but now I have a question to answer from you. In your first proposal, you have changed a software to conduct a structural analysis, which lowers the modal frequencies. And if I look at figure 19 in your proposal, you also show some one result. Yes, this one here. The power of the station is confined in the upper half of the spacecraft. Right? And is this a common feature? Do you have a similar structure in your previous calculation using CATMA? Just I want to know your answer. Or in other words, the validity of your software and the previous software. Which one is really better?
In the previous report, we utilized CATIA to perform analysis, and this time we use Abacus. And the difference depends on the mesh. The size of mesh will influence the result of the analysis.
Okay, and also I remember that now you use the honeycomb structure in your new model, and does that also modify the result?
Yes. We in analysis we didn't include honeycomb structure.
Since the honeycomb structure is a non-homogeneous material, it is very hard for our PC computer to analyze its random vibration or quasi-static acceleration. Yes, it beyond our ability. Yes.
Okay, I have a question. Two questions. I missed to hear the thermal environment, about the thermal environment. Which is the lowest temperature case and highest temperature case during the entire mission? For example, I think the thermal environment drastically changes near the Earth's orbit and in the lunar environment. The coldest case and hottest case.
The hottest case occurs when the thruster is turned on, and we need to deploy radiator to transform heat from tank to environment.
No, I mean that during your mission, the thermal environment changes. For example, in the near Earth orbit, you may come across, you may suffer from albedo radiation from Earth as well. And in lunar environment, the heating environment changes from that of near the Earth orbit. So, which is the coldest environment and hottest environment you have done in your thermal analysis? Otherwise, you can't estimate the range of temperature.
Our group member can answer the question.
cruise phase, and the hottest happen at the structure will turn on.
Okay.
And the cold case is the distance between Earth and the Moon. It's because the planet will radiate the hot through satellite.
Thank you.
I would like to ask you about the summer relating to this question. And how do you treat summer dissipation of ion thruster? Ion thruster is a very large heat dissipation, and you modify or change the value of dissipation heat. Previously, you signified the value of 1 kilowatt, but finally you changed 495 or half of the heat. How do you treat? I think it's a deployable radiator. Is that okay? Right?
You say radiator?
Deployable heat radiator.
Yeah.
In the previous section, we used the thruster of 40 millinewton, and now we use the thruster of 15 millinewton. So the heat dissipation will be lower. And since there are many space missions also employed the radiator design, so we think to use the radiator is okay.
And so your ion thruster is always operated?
No. To ensure that we have enough battery power, our thruster will open for 4 hours and then turn on and then turn off for 4.5 hours and then turn on for 4 hours. It will turn on periodically.
Periodically?
Yes,
so
to charge the battery, and also the temperature will be lower.
Deployable radiator can open and close?
No, the radiator
If it
will
opens,
open.
not close.
Yes, it will not close. It will not close. It will just open and it will just deploy and through the whole journey.
And then the radiator area is large, so it means radiation amount is larger. So if the environment is a very cold case, the heater should be operating. How you calculate the amount heat of the dissipation in your analysis?
Okay, so sorry, sir, I'll explain it. When the hot case, the thruster will turn on, and the radiator also turn on, and radiate the heat to the space. And when the thruster will close, and the radiator also close to x direction, and get the heat from the sun.
So the deployable radiator, if it's open, it could not be closed in the future.
Do you use a deployable?
Yes. I use deployable radiator.
And you are opening and closing?
Yes, periodically.
Open and closing?
Yes.
I see. now you have added a new instrument, SHP, that can measure the solar UV flux, which I think certainly increase the significance of your mission. Now, can you measure the spectrum of UV radiation with this instrument, or you can just measure the integrated intensity in this spectrum? I mean, the spectrum, intensity as a function of wavelength, or just you can get the integrated flux.
Let our members answer these questions.
The major principle of the instrument shape is that it's the photocurrent. We have two kinds of metal on it, which in this case is tin and gold, and their work functions are different. And so when the photon with the energy higher than its work function, it will generate the photocurrent. However, any of the photons which have higher energy than its work function can generate photocurrent. So it means that we can't tell which exactly the wavelength or energy the photon is. So we can only know the intensity, but we don't know the spectrum.
I see. Yes, I see.
So I have a question about link budget analysis for communication. So I commented uplink link budget about maybe pointing loss of a ground station. You wrote 40 dB loss about.
Oh, you mean the DSN's path loss?
Yes. No, pointing.
DSN's pointing loss. Well, I get the information from the DSN's properties on the internet. That it says the DSN's pointing loss is exactly about 40 dB. So it's from the internet's information.
But I think 40 dB loss is very large. And maybe I would miss something, but in your updated proposal, so one link budget analysis on downlink is missing. So no chart in the proposal. Why?
We remove the uplink margin of the link budget because we think that the uplink is more responsibility to the ground stations. So it's not our satellites' work. The only work our satellites have to do is to receive the signal from DSN, and how DSN will perform depends on DSN itself. So
And also, we think that since DSN has enough power to transmit the signal to Earth, we don't think it's a big problem in our link budget.
I could understand what you want to say, but maybe at least the feasibility, one of the feasibility, you should show this kind of chart with something unknown, unconfirmed parameters. So maybe you should add uplink budget in this proposal.
Thank you.
Let me ask you about the attitude control system. If I correctly remember, probably you didn't talk about the unloading of the reaction wheel. Have you designed the unloading system? reaction tree will saturate in the course of absorbing the angular momentum. So you need some kind of unloading or desaturation system.
Do you have propulsion system? Gas-type propulsion or ion engine only?
Did you mean that the propulsion will cause the attitude of the zeta to change?
To unload the momentum wheel, one approach is to use a gas propulsion system. The question is how to unload.
We don't utilize unload system.
Okay, probably it's not very difficult task, so I recommend you try to design the unloading system.
Okay, thank you.
ありがとうございました。ここで質疑応答を終了とさせていただきます。大学の皆さん、ありがとうございました。以上で全ての作品の発表が終了しました。